In this work, we present balanced MSE for imbalanced visual regression. In short, balanced MSE is a statistically grounded loss function to address the train-test mismatch in imbalanced regression. This is an overview of this presentation. We will first discuss why imbalanced visual regression is important. Data imbalance is common in real-world applications. In age estimation, most photos are from adults and relatively few photos are from children and senior adults. As a result, a model will underperform on minority groups. This hurts the model's fairness and generalizability. Compared to imbalanced classification, imbalanced regression is more challenging for having a continuous and sometimes high-dimensional label space. For example, the parametric human model SIMPLE has an 82-dimensional label space. What are existing strategies for imbalanced regression? A popular line of work is based on synthesizing minority data. However, synthesis-based methods like SMOGAN are hard to be applied to high-dimensional data like images. Recent works focus on estimating training label distribution and reweighting. For example, deep imbalanced regression uses kernel density estimation to interpolate and extrapolate the label distribution. However, we show that reweighting fails even when true label distribution is known. In this linear regression case study, reweighting fails to find the ground truth. In summary, imbalanced regression is important in real-world applications but lacks an effective approach. We propose balanced MSE to mitigate the gap. We start by revisiting MSE from a statistical perspective. Mean square error is the most common loss function in regression tasks. From a statistical perspective, MSE can be equivalent to the negative log likelihood, where the regressor output is the Gaussian mean. However, when the training label is imbalanced and the testing label is balanced, we will have a train-test mismatch. The mismatch is proportional to the ratio between the label distributions. Therefore, a regressor trained with MSE will underestimate rare labels. To address this mismatch, we propose balanced MSE. We let the model directly estimate the balanced conditional probability and do a statistical conversion during training. We name the negative log likelihood of the converted probability as balanced MSE. Bringing the Gaussian prediction distribution into the statistical conversion, we obtain the final form of balanced MSE. It consists of two terms, an MSE term and a balancing term. When the training distribution is balanced, the balancing term will be a constant, and the loss degrades to the standard MSE. Note that there is an integral in the balancing term. It can be hard to compute in practice. Therefore, we provide both analytical and numerical implementation options for the integral. For the analytical solution, we use GMM to feed the training label distribution. The advantage of employing GMM is the fact that the product of two Gaussians is an unnormalized Gaussian. Therefore, the integral can be analytically solved. For the numerical solution, we use the Monte Carlo method to approximate the training label distribution. We treat labels in a training batch as random samples from the label distribution. Then, balanced MSE can be written in a softmax way. Most importantly, this loss function is easy to implement and requires no label prior beforehand. We demonstrate the effectiveness of balanced MSE on both synthetic and real-world benchmarks. On the synthetic benchmark, we visualize linear, nonlinear, and multidimensional regression. The regression result of balanced MSE is very close to the oracle. By contrast, the standard MSE and reweighting fail to find the oracle. On the real-world age estimation benchmark, balanced MSE achieves the state-of-the-art results. We visualize the performance gain across all ages and observe that balanced MSE substantially reduces the prediction error on minority groups like children and senior adults. We also propose a new real-world benchmark for multidimensional imbalanced regression on human mesh recovery. Again, balanced MSE achieves the best results. Qualitatively, it eliminates the bias towards the mean pose and effectively recovers rare poses. In conclusion, we revisit MSE and identify its ineffectiveness in imbalanced regression. We thus propose a statistically grounded loss function which outperforms existing methods on various uni and multidimensional imbalanced regression benchmarks. Thank you for watching.